Hi everyone, welcome back to another session of Math 273. Today we're going to continue our talk about ANOVA, analysis of variance. I know it's been a bit since we last had a video like this due to the midterm exam and the fall break that we had. So hopefully that gives you guys some time to rest up and get ready for the second half of the semester here. So as a quick reminder, last time we talked about this one-way ANOVA model formulation, which is just a way to test if the average response value differs across several groups, typically 3 or more groups. So it's a bit of a different approach than a regression approach, but the results are actually equivalent to using a categorical predictor that has multiple levels and comparing the response value across those levels of the group variable. But it's good to understand the formulation of an ANOVA model using an ANOVA for analysis because a lot of people use it in research and analyses, and so the results are sort of presented slightly different. So we're still going through it so that we can understand other people's work when they do this. Although certainly want to note that you can always just use regression with a categorical predictor instead of ANOVA. They're equivalent. So anyway, continuing with ANOVA for today. Some notation here, we just define y bar is going to be the sample response value for the whole data set. Alpha sub k, as a reminder, are these group effects. So the difference in the average response value for a particular group and the overall group sample mean. So we denote this by alpha sub k with a hat because it's for the sample. It's a sample estimate. And then this y bar sub k is representing the group specific sample mean. And again, this y bar is the overall sample mean for the whole data set. Okay. And then just like in regression, we actually get errors or residuals for each observation as well. And so we define it for the group effects formulation as being just each response value for the observation minus its corresponding sample group mean. Just like in multiple linear regression, we actually have this ANOVA table. And so this is more commonly what people are referring to when they say ANOVA, I think, but there's also that ANOVA formulation that we looked at before, like I said. But again, this ANOVA table we use to test for any difference in the average response value across groups. And so just like in multiple linear regression, what we look at is the p-value, which is calculated based on the F test statistic. And a lot of these values are the same, actually interpreted as being the same. So we have the sum of squared errors, SSE, sum of squared total, SS total, sum of squared groups, which is how much variability is explained by the groups. So a lot of these values are the same. MSE is mean squared error. And again, we can use it to test for an overall difference in the group means, or equivalently, test if the group effects are all 0. Essentially, is the mean the same across all groups? That's the case if the group effects are all 0. And so comparing our p-value at 0.05, we can test this at the 5% significance level as per usual. So just like multiple linear regression, we have certain assumptions or conditions that are met in order for our model to be valid again. And these assumptions actually are quite similar to regression, which again has to do with them being equivalent, like the results are going to be implying the same thing. And again, just like regression, these assumptions pertain to the error term. So errors must have mean 0, which they usually do by construction. We have to have the same standard deviation within each group for the residuals. So this is that homoscedasticity assumption again. we need the errors to be normally distributed, and we need them to be independent. So we check these with the same plots as before, each of these assumptions. And sometimes people write all three of these assumptions more concisely as just saying epsilon is distributed independently, normal with mean 0, and the same standard deviation, sigma sub epsilon. So that's sort of using like statistical theory notation, I guess, to declare all of these three assumptions simultaneously. You guys don't need to know how to write that, but just in case you ever come across that. Okay, so for checking that equal variances assumption, we can again, just like regression, plot the residual by fitted values. Looking at that plot, and we just want to see that constant spread across time, across the x-axis, no fanning or any sort of weird patterns. Another thing they do for ANOVA more commonly is looking at, since we just have these groups always, and we need equal variances of the residuals within each group, what people do is they can, you can calculate the standard deviation for each group, and then get the max standard deviation across the groups and the min of those standard deviations. And we want the ratio of them to be less than 2. The idea being the group with the most variability and then the group with the least variability, we don't want them to be that different. So we want the ratio of their standard deviations to be less than 2. And again, that's sort of just a rule of thumb. Like, it's not that magically, if it's less than 2, if this ratio is 1.99, it's not that it's magically, the assumptions aren't magically met. It's just, this is sort of just a rule of thumb for decision making, for seeing if there's a problem or not in terms of equal variances. Okay, and so we're going to look at the penguins data set again to see how we can check these assumptions. So we're going to look at comparing the average bill length, that's our response variable, across different levels of a group, which is going to be the species of the penguin. Okay, and then looking at this residual by fitted plot, here we can check the equal variances assumption. We can also look for potential violations of independence. Like, we still want the residuals to be independent. So we wouldn't want all the residuals to be more positive over here and then slightly more negative over here. We wouldn't want that to happen. So we want this like sort of random scattering centered at 0 within each group. And that looks pretty reasonable here. The spread is not too much different within each group. They're shifted a little bit, but not bad. So yeah, I would say because this range of values within each group is fairly consistent, constant variance appears to be met. Another thing to mention, I don't think independence looks questionable here at all. It seems fine. So, all right, and then another way to double check that constant variance assumption, I'm using this tapply function in R. So here we put the response value vector here, and then a grouping variable here, a vector indicating the group level memberships. And then I say which function I want to apply to the response value within each group. Okay, and that's what fun stands for, is function. So I'm applying the standard deviation function, SD. Then I also just gave it the argument to say remove NA values, remove missing values equals true. Okay, so that gives me, this was essentially a vector of length 3 that contains the 3 standard deviations, one for each species of penguin. And then I can get the max of those 3 standard deviations divided by the min, and I look at the ratio here, 1.25, so that's less than 2. So that also indicates that the constant variance assumption is met. Okay, and then another assumption was the normality of the errors. So looking at a QQ plot again, just like in regression, we want the points to fall mostly along this dotted line through the origin here. So this is certainly fine here. None of the points stray very far. This one, 186, which is telling us the observation number, I think, in the data set, is a little bit far away from the dotted line, but it's only 1 point and it's not too egregious. It's not too bad. So certainly this plot indicates that normality appears to be met for the residuals. Okay, so overall, the assumptions appear to be met here for this penguins data set. But let's look at an example where these assumptions are more problematic, so they're not potentially met. And what we're going to look at is an example data set on cancer survivability from the textbook. So here they have 64 observations on just 2 variables, which is the survival time, how long a person survived, given their cancer diagnosis, and then the type of cancer that they had. So this is defined by like which organ the cancer was identified in, I believe. Okay, and so we have 5 different types of cancer here. So I load the data set. It's one of the data sets that are pre-packaged into the Stat2 data package. And then just taking a look, we see how many observations there are for each cancer type. So not a ton here. It's a pretty small data set relative to other ones we've looked at. So we'll keep that in mind moving forward. Here to fit a ANOVA model, a one-way ANOVA model, where we want to see if the average number of days survived differs by the type of cancer. So we're just going to do survival, our response variable, tilde, organ, our grouping variable. Okay, and then we're going to use the AOV function to fit this ANOVA model. And plotting that output, R doesn't make it look as pretty as the regression output, but we can sort of see this is the ANOVA table here, this degrees of freedom column, SS, mean square, F-test statistic, and what we're interested in most, the p-value here. So this p-value is very small, 0.000229. So interpreting this result, here we can say that since the p-value is less than 0.05, we have evidence at the 5% significant level that the mean number of days survived differs by cancer type. Okay, so we don't know which cancer type has like the highest survival, which one has the lowest. We just know that they're not the same. That's all this result is telling us. But are the model assumptions met? We actually didn't check that first yet. We just sort of jumped into running the ANOVA, but that's something we should check here. And in general, I want to mention that for regression and ANOVA like this, when you have a response, if it's something that is always positive, so in this case, like the response variable is the number of days survived. So that has to be something that's always positive. It can never be a negative value. And it can only just keep getting, like values are not really, I mean, technically they're bounded, but you can keep getting survivals that are really, really big if somebody just lives a very long time. So you can get values that are going to be very, very far outliers potentially. In these sorts of cases where you have values that are guaranteed to be positive and can just, there's not really a hard limit on how big they can be, this tends to be situations in which assumptions can be violated due to the distribution of the data not being, I guess it's I'm not sure exactly why, but it tends to have assumptions being violated more often than not in these types of data. And we'll see that going on here. So looking at the residual by fitted plot here, we can see that there's this fanning of the residuals. So this is indicating that constant variance is not met because we have this fanning shape where the spread or the variability in the residuals is bigger for bigger fitted values and smaller, the variability or the spread is smaller for smaller fitted values. Okay. So this indicates that constant variance of the errors is not met. Also looking at that ratio of the standard deviations, very problematic here. So we got 5.9. It's supposed to be less than 2 by that rule of thumb. This is way bigger, so it certainly is indicating that constant variance is not met as well. Okay. Even though constant variance was not met, just for the heck of it, looking at normality here by looking at the QQ plot, this is not good. This is, we have these tails, which is what you'll most commonly see when this assumption is violated, is that the tails are straying far away from the dotted line through the origin. So here, all of these points are sort of off. These points are off. So this is indicating that also normality of the residuals is very questionable here. Does not appear to be met. Okay. And Pikachu is very concerned about these assumptions not being met. We went ahead and fit the model anyway. So you can see he's can't believe it. He can't believe we did that. But fortunately, we're not done. We can try and fix this. So we're going to log transform the survival time and see if this helps the assumptions be met. So here's a plot of just the raw untransformed survival times. So this is where I was talking about you can get values that are very, very big because someone survived for 4,000 days. So it ends up with this sort of skewed distribution. And it's not that we need the raw transformed values to be normal exactly. We're looking at the residuals for the assumptions being normal. But usually, again, if the raw response values are looking very skewed like this and not normal, it'll often be the case that the residuals are not looking normal as well. So anyway, so looking at this plot, it's not a very nice bell curve shape, but if we log transform, we get this nice bell curve looking thing instead. So this seems much more promising for our assumptions to be met here. Okay, refitting the ANOVA model, we get a p-value again, very much smaller than 0.05. So interpreting this, it's a little bit different because now we're talking about mean survival, but actually it's sort of very similar to last time, so I'll just copy it. All right. Okay. Okay. So since the p-value of 0.00412, we have evidence at the 5% significance level that the mean, we'll say log days survived, so differs by cancer type. And so we lose a little bit of interpretability here because we're talking about the log days survived, not just the days survived between the groups. That's sort of a drawback. There's trade-offs. We lose a little bit of interpretability, but our inference is now going to be valid. Our p-values, confidence intervals, and stuff that we calculate relative to this model are now valid, assuming our assumptions are met. So checking these assumptions here, we see that this constant variance assumption appears much better. So it's not perfect again, but looking at the spread within each group, it's much more similar after the log transformation. So this seems to indicate that constant variance is met. And again, looking at that ratio of the standard deviations, now we pulled that below 2 after the log transform. So 1.72 less than 2. So this indicates that the constant variance assumption is met as well. So that seems to have been fixed with the log transformation, which is great. Looking at the QQ plot, here again, it's not perfect, but the number of points straying far from the dotted line is less. And also the amount that they're straying away, the distance away that they're from the dotted line here is not as bad either. So normality appears to be much better here now. So overall, we'd say assumptions are met based on these plots, and we've made Pikachu happy, no longer fitting these invalid ANOVA models. So from the results of this, so we determined that at least one group differs in its average log survival across the different cancer types, but we may naturally, it would make sense, we want to know which cancer type has the worst survival, which one has the best survival. And so how do we do that? ANOVA doesn't directly allow us to do that, but there's this approach, this analysis approach called Fischers least squares difference, LSD. Okay, and Fischer is the same guy who is the one who came up with the rule of thumb for why we compare to 0.05. So, so investigating this further, we can use this Fisher's LSD, least squares difference, or confidence intervals for the response values for each group, for the difference in the response values between each group. So for a 95% confidence interval, a pair of group means are only different at the 5% significance level if the confidence interval for their difference excludes 0. Okay, because if 0 is in the confidence interval, then it's a reasonable possibility that the groups are the same, that the difference in their means is 0. But in general, we should adjust for multiple comparisons when calculating a bunch of confidence intervals, because there's potentially a lot of pairwise group comparisons to be done here. It's not just one confidence interval. We might compare for the cancer subtypes. Let's see, there was like 5 different cancer subtypes. So we might compare like ovary and stomach cancer, but then we also might compare bronchus and colon cancer. So that's already 2 comparisons. Then we can compare breast cancer and bronchus cancer. So there gets to be a lot of different pairs here. Each time we're only using 95% confidence. It's sort of one of those things, the more you do, the more intervals you calculate, the more likely it is that one of them is going to be wrong, just because you've done so many of them. So we need to adjust for that so that we can still be confident that our intervals are reflecting the truth. Okay. And sometimes they call this like a multiple comparisons adjustment or a multiplicity adjustment. So Fisher's LSD uses a modified confidence interval to account for these multiple comparisons. So specifically, we have for the ith group, there's sample mean response. The jth group, there's sample mean response. And then the difference between them, plus or minus this margin of error, which is a t-star multiplier the same as we've seen previously, times the square root of the MSE from the ANOVA table, and then 1 over the number of observations in the ith group, plus 1 over the number of observations in the jth group. Okay. So this is the confidence interval formula for a Fischers least squares difference confidence interval. And we only do this Fischers LSD if we found a group difference from the ANOVA test. So we only get to this step if we found at least one of the groups differs. Otherwise, if we found that all the groups were the same, or we didn't have evidence that any of them differed, we don't even bother with the group comparisons because we already tested if they were all the same or not. Okay, so if the sample means we already, or the true population means we concluded we didn't have evidence that they differed, we shouldn't bother with this test. This is only if we got a statistically significant result from our ANOVA test. Okay, and as I mentioned, that term to the right, the t star times the square root of the MSE times the sample sizes here, is the margin of error term. And actually for Fischers LSD, this is representing the smallest difference between the group means, such that they can be considered significantly different. That's how that's interpreted here. Okay, so we'll look at doing just one comparison for this survival data set. Specifically, we're going to look at, do people with colon cancer have a different expected survival than those with stomach cancer? So here's our formal statement of our hypotheses, so that the average survival time is the same and that it's different. This is our alternative hypothesis and our null hypothesis here. Okay, so first, just looking at the data set, we get the average survival time for each cancer type using this t-apply function again. And this is the average log survival time, because that was what our assumptions were checked for. Okay, and we see we're comparing colon and stomach. So colon has a little bit higher, 5.75 about, compared to 4.97 about than stomach. So, but is it different enough? They're kind of similar. So we're going to use this Fischers LSD to formally look at that. From the ANOVA table before, we're not going to scroll all the way back, but we had the MSE was 1.428. Our T star, which you can calculate using R, using that QT function in R, is 2.001. And using these values, along with the sample means and the number of observations in each group, so we have 17 observations for colon cancer, 13 for stomach cancer. So we use those for our NI and NJ. T star we had up there in the MSE. Putting those all together, we can calculate that the LSD is about 0.881. Okay, so the 95% confidence interval for the difference in the average log survival time between the two groups gives us this. So we have a negative value and a positive value. So 0 is included in our interval. So we want to think about what that means. So since 0 is included in our interval, we cannot conclude, we do not have evidence that there's a difference in the log survival between the two groups. That's what that means. Okay, so we actually won't even bother interpreting it here. But so in other words, we did not find a difference in the average average log survival time between those with colon cancer and those with stomach cancer. Okay. All right, so that's all for ANOVA today, and there'll be another video on Wednesday. So thanks, guys.